Okay everyone, this is the flipped video lesson on geometry, part 1. Now, this video is for both Math 7 and 7 Plus, but the entire video is not for Math 7. So look for the slide where I say Math 7 stop, which will be in a while. And if you are in 7, then you can stop. You can certainly watch it, because the content you'll eventually have to do, but you don't have to do it right now. Of course, Math 7 students, you are responsible for watching the entire video. This unit is one of several. You have 3 in geometry. In this unit, you will review triangles, angles, and some other things with shapes. Now, I'm going to be honest, I get really excited with geometry. When I was in school, and I was in high school, if you remember, I divided up in class. I know I did this with third period, all the different types of math. You have basic computational math, followed by algebra. Algebra then goes into functions, which would be linear, quadratic, exponential. And then you've got the next level of geometry. And then geometry branches off into trigonometry, which is the math of triangles. And then the highest math, of course, is calculus. When I was in school, geometry was my easiest subject in math because I could see it and color it. And coloring it makes it so much easier to see. So have your coloring pencils or highlighters with you every day, which you should anyway, but make sure that you have them, especially now, because it will help tremendously in working with the geometry unit. Last year, you learned that a triangle has the following characteristics besides being a 3-sided shape. If any of these do not look familiar, however, make sure you pay special attention to what you're unfamiliar with to ensure you being successful. Okay, all triangles, no matter what they look like, always add up to equal 180 degrees by adding the 3 inside angles of that triangle. It does not matter how weird that triangle looks. It could look like that. It could look like this. It could look like that. I could go on and on and on. But if you add up all 3 of these angles, they're always going to be 180 degrees. That's one of the rules of a triangle. A quadrilateral, by the way, is worth 360 degrees. And that would include a square, rectangle, rhombus, parallelogram, diamond, or a quadrilateral. Okay, now let's get into specifics of triangles. First, we have equilaterals, which is when all the side lengths measure the same length, and your triangle angle measurements are each 60 degrees, because 180 divided by 3 equals 60. Isosceles triangles are when you have 2 angles and 2 sides that are equal. So that leaves you a third angle and side length, which it looks weird. An example of what isosceles look like, it could be really fat looking like this, or it could be super, super narrow. But you would still have, like I said, 2 side lengths and 2 angles that are congruent. Right triangles means one of those angles measures 90 degrees. It looks perpendicular. A scalene triangle is when all 3 of your angles are under 90. And an obtuse triangle is when one of your angles is equal to or more than 90. So an obtuse triangle looks like this. So the little 2 ones are smaller because this big one is more than 90 degrees. With this information about these specific kinds of triangles, you will be asked to experiment drawing different triangles given measurements to determine if the information given to you will make a triangle or not. To do that, however, let's look at some more vocabulary. Parallel lines are lines that never intersect. Perpendicular lines make 90-degree angles. Complementary angles add together to create a 90-degree angle. And supplementary angles measure out to be 180. So if you add those up, it's going to be 180 degrees. Here are some examples of what to do. Can a triangle have more than one 90-degree plus angle? What shape can you make if it's a quadrilateral with parallel lines but no right angles? And then look at any of these measurements, which one or ones would make a triangle and which ones wouldn't. The length measurements are 13, 5, and 6, 3, 3, and 3, and 2, 7, and 6. Here's the hint. The two smaller lengths must be more than the longest length. So, the biggest here is 13, and then you've got 5 and 6. 5 and 6 means 11. That triangle won't work. 3, 3, and 3. That'll work. That's an equilateral triangle. 2, 7, and 6. Okay, my biggest one was 7, then I had 2 and 6. Well, 2 and 6 is 8, so that one also will work. Up here, can a triangle have more than one 90-degree angle? The answer is no, it cannot. So if you have a big obtuse triangle like this, the two little angles must add up to be it would be 180 minus this big angle divided by 2. That number's never going to be bigger than 90, because 90 and 90 together is 180, which that's what a triangle is, but that's only two angles, so it just doesn't work. And again, what shape can you make if it's a quadrilateral with parallel lines and no right angles? So remember, a quadrilateral is a four-sided shape. Well, that takes out a rectangle and a square because they have right angles, but a parallelogram will work because these lines are parallel. They'll never touch, but they're not 90 degrees. And rhombuses will work as well. Moving shapes around a coordinate plane is called a transformation. There are multiple kinds of transformations. They include reflections, rotations, dilations, and translations. Translation and transformation sound really similar. So I'm going to show you examples of what they look like. Okay, here I have a triangle written for you. And this symbol right here, remember, is sigma. And sigma means the sum. So I've done this as shorthand. And this shape right there, that is the abbreviation for an angle. Sometimes in school you will also see an angle designated looking like this, but most of the time you see it like this. Remember that the sum of all three angles in a triangle equal 180. You can manually measure two of the angles and figure out the third easily. You don't have to measure out all three. All you need is two, add those up, and then subtract that sum from 180 and you're good to go. So in this instance, what I did is I measured the first angle. So this angle is worth 68 and 2/10 degrees. I used a protractor on my app to figure that out. And over here, I calculated 46 and 62 hundredths is my measurement. Well, if I add those up, 68 and 2/10 plus 46 and 62 hundredths, then I subtract that sum from 180. My third measurement here, this angle would be worth 65 and 18 hundredths. Now this is super specific because my app did it with the protractor. You can round off angle measurements to the nearest whole number. So if I had done that, this would have been 68 and 47, and then I would have gotten a very comparable number. It's not a big deal. Here are illustrations of those different triangles. Scalene looks like this: isosceles, equilateral, obtuse, and right. Now, let me show you some other measurement or little signatures here. See these two lines in the isosceles? That's saying that those two legs or lengths are equal to each other. And an equilateral, you see it three different ways because all three are the same. And here's a term that you may not be familiar with. Equal and congruent mean the same thing. This is equal and this is congruent. I'm going to use these words interchangeably, and you are responsible for knowing that they both mean the same thing. Here's another example. In addition to the sums of triangle angles measuring 180, straight lines also share this. The measurement of a straight line is worth 180 degrees. So a triangle and a straight line both equal 180 degrees. Now, why is that? Well, if you have a triangle here, and if you lay out all of those, it equals out to be 180. That's why. So, in this one, I've got a set of lines, and I'm trying to figure out a value of a different angle. So, in this picture, lines AB and CD are parallel. Triangle GEI has one right angle. Angle I also has a measurement of 40 degrees. From this, you can calculate the angle of X. Now, this angle right here is worth 90 degrees. Okay? That's important. And I'm going to show you exactly why color helps so much in this instance. So here's my 90-degree angle here. So I can then calculate this one because I was given 40 up here. Well, 90 plus 40 is 130 degrees. That means that, I will change colors here. That means this angle right here, that one's worth 50 because 50, 40, and 90 all add up to be 180. Now, I'm being asked to calculate this X angle, which is this. Well, a straight line is worth 180 degrees. Well, if I knew that the red portion was 50, 180 minus 50 is going to give me 130. And we're going to practice this in class too, but that is how it works out. Here's another example. How do you find angle X? Okay. When lines cross as you see here, the angles on opposite sides become congruent. This is an important hack when figuring out unknown measurements. Okay, this is what that means, and let me show you by color what I'm talking about. You've got two lines that are intersecting right there. I don't know right now how much those angles measure, but I do know that they intersect. A law of geometry means that if two lines cross, opposite angles are congruent. That means this angle here is equal to the one that's opposite to it. And the same would be true for the other pair. This one is congruent to this one. It's a really cool law of geometry. So, in this example, I have a triangle. This angle measurement is 30, and that angle measurement is 30. I'm being asked to calculate X. Well, I don't know what X is, but I can figure out pretty easily what this one is, which happens to be congruent to X. Well, 30 and 30 is 60. 180 take away 60 leaves me with 120 degrees. That also makes that measurement 120 because they were congruent to each other. Now I'm going to show that real quick here. You could also follow those other triangle measurements were 30 degrees too, but that we're not being asked to do that in this question. Here's another question. What are the measurements of angles H and A? So now I've got two. Okay, so let's look carefully. I'm being asked to figure out H and A. I'm given one measurement, which is 75. So with that information, I can figure out what the sum of A and H equal. A and H would be, together, would be 180 minus 75. And that would be 105 degrees, both of those. but I am given some other information. Remember that a straight line measures 180. I've got 45, and I've got 50. Well, 45 plus 50 is 85. I'm sorry, I did that wrong in my head. 50 and 45 is 95 degrees. But a straight line is the difference of that. So 180 minus 95 gives me 85. So the measurement of angle H is 85 degrees. Now I can figure out A pretty easily, which would be 180 minus 85 minus 75. That difference is 20 degrees, so that's the measurement for angle A. Now, angle A looks a lot bigger than 20 degrees. That's because this is not to scale. And you need to know that sometimes the diagrams given on a test are not accurately drawn. They do that to trick you because they want you to go with not what it looks like, but how you can prove an answer using rules of geometry. Here's a much clearer of what that triangle from the previous question would have looked like drawn to scale, and it looks really different compared to the first one I showed you. Okay, prove without measurements that angles 3, 4, and 5 equal 180 degrees. Well, let's first mark what they are. Line L and M are parallel to each other. When you have a set of parallel lines, I'm going to draw a different example over here. Let's say I've got these two lines that are parallel. And then I have a line that goes through it like that. If I have a line that goes through it, we call that a transversal. And transversals have some really cool rules with it. Some of those rules are this angle and that angle are congruent. That means the ones underneath it also are congruent. That also means these two angles are congruent as well as the pair underneath it. And coloring it out will make that a lot easier to see. So right now, in this example, I've got two transversals. I'm being asked to say 3, 4, and 5 add up to be 180 degrees. So let me mark those real fast. 3, 4, and 5. Now, the rule of a triangle is that all three of those equal 180, but that isn't the only way to do it. I can still prove it. Since a straight line and a triangle measure to equal 180 degrees, you can prove that the angles create a triangle. If I added 1, 2, and 3 together, that would be 180. Angle 2 and angle 4 are congruent, and angle 5 and angle 1 are congruent. So, what that is saying is this. I can calculate the following information based on what this is. All right? I'm given 1, 2, and 3. If I added 1, 2, and 3 together, that's going to equal 180 degrees. Okay? Angles 1 and 5 are congruent. Angles 2 and 4 are also congruent. And since a straight line and a triangle equal that, that's how I could have proven that that all equals to be 180. And when you're given numbers to work with this, it also will work, and we'll do examples of that in class too. Like I said, I just wanted to give you a visual example. In this question, I'm being asked to calculate what are the measurements of angle A, B, and C, which are designated up here. And I'm going to color them differently. So that's A, B, and C. I was given angle Y and angle Z. So with this information, I can figure out A and B and C using all those different cool transversal things. Let me start first with angle B. Okay. Angle B can be calculated by finding the leftover amount of 180 degrees minus angle Y, which was 35, minus angle Z, which was 80. 80 and 35 added together is going to be 115. And then 115, 180 minus 115, that's going to give me 65 degrees. So now I've got angle B, no problem. Remember that lines, I can show that different angles are congruent to each other. That means that this angle here is congruent to this angle over there. So if this one's 80, so is C. So now I can calculate A by either adding 80 and 65 together and then subtracting that amount from 180 degrees, and then I'll be good to go. So 65 and 80 added together minus 180 is going to give me a measurement of 35. I could have also done it with this. I could also, using the rule I just did before, remember I said that this angle, the blue ones were congruent, so is this one. This one's congruent to that. So if this one's 35, so will that one. So that gives you all of your different angle measurements. And remember that I could have only done this because in my question I was given over here on the side that this line and this line were parallel. If they're not parallel, can't use the transversal rules that I had explained. Okay, that slide is the end for Math 7. Math 7 Plus, please continue. We're going to start working with the transformations, and the transformations include dilations, translations, reflections, and rotations. Okay. Translation is when you move a shape. And this is always done on a coordinate plane. So translations mean, and this may sound kind of funny, but it means that you are moving them. Translations and dilations usually mean the same thing. A reflection is a mirror image across either the Y or X axis, and a rotation means to turn it like a tire. That's why they call it rotations. So, are these polygons congruent? Is this polygon congruent to that one? And I can prove that by where it moved. It moved 5 spaces to the right and 2 spaces down. The reason I got those numbers is by this. I pick a point and then I find that same point on the other shape. And that was 1, 2, 3, 4, 5, and then 2 down. I can't change the points. Otherwise, I'm going to get a really weird answer. I could have picked that one, but then I would have also had to pick that one. And conversely, this one versus this, or that versus that. I can't mix them up as I go along. Okay. In this question, you are being asked, did this original rectangle get rotated? And if so, by how much? And the question is, it did. And it got rotated 90 degrees. And that is done by basically spinning this around. See how this shape, this point is that point, and that point got moved there. that would have given you this going here, and finally this point went there. In this example, I'm being asked what happened, and this was what we call a dilation or a translation. I'm going to pick this point. This was my first triangle. So to show how far it moved, it went to the left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it went 10 left. And it went 1, 2, 3, 4, 5 down. And that's going to be true for any of the points in this triangle. I could have chosen, like I said, I could have picked starting here and there, or the other one. But remember, like I said, you can't change them up. This is showing a picture. Now this one is, I'm being asked to reflect. And I'm reflecting across the y-axis. That means I need to create a mirror image of this triangle over here and this triangle over here. And that's what they look like. If you go back, you can see. This is a rotation. And we need to see where it ends up. So it's starting here. And it ended up over here. So remember that it originally was located there. And I spun it around. I'm going to show that by this going around to here. That got flipped. If it had been here, it would have been, that would have been a 90-degree rotation. But since I went to these points, it ended up being a 180-degree rotation. One of the rules of a circle is that a circle can rotate 360 degrees. It's just, you can't find what the individual angles in a circle are. You can't do that. But when you're using rotations, it enables you to go all the way around. So a 360-degree turn, for example, means it went all the way around one revolution. That's where that circle movement's making. If it did a 180, then it got turned. You hear that driving sometimes, like if you have a car here and then it spins around, like if this is the front and then it spins around to where that's the front, that's a 180-degree turn. Whereas if it goes all the way around and it ends where it's started, that would be a 360. That happens a lot when cars are driving on ice and they lose traction. Okay, dilations can also mean scale factor changes. And in this instance, I'm doing a dilation with a scale factor of 1. That means I'm increasing each measurement by 1. And we talked about this before the grading period ended, the second quarter, because if you are, let's say, doubling it, people will draw a triangle that's double, but it's really supposed to be 4 times bigger. And to prove that, look at your side measurements. This one was 5 and 4. So doubled 4 is 8, and 5 doubled is 10. Do not try and count the length of that diagonal line, especially if it's a right triangle. You have to use something called Pythagorean theorem to calculate the length. You just can't count going across. It would give you a close answer, but it's not an accurate answer. So only go with the sides that are you can easily measure which were the other 2 lengths. This is a dilation example with a scale factor of 1/2. And to do that, I would look at my original triangle, which is here. This had 6 and 4, and half of 6 is 3, and half of 4 is 2. So that little triangle is formed. Here's the difference between a concept called similar versus congruent. The congruent symbol means, like I said, equal. But then there's this other called similar. Similar means that something is proportional. And you have to prove that it's proportional mathematically for it to work. These triangles are similar because they are proportional to each other, and they are proportional by the scale factor reduction that I showed. Describe what happens with these shapes. What types of transformations do you see? So my original is this little triangle right here. And watch what happens. That is what the reflection of that little triangle looked across the x-axis. So my original triangle was here, and my reflection is here. A dilation of 1 rotated 180 degrees around the origin. Okay, when you hear something called around the origin, they are saying there. So imagine that you're spinning this triangle. So watch. This got rotated to that point. This got rotated to this point, and then that one went here. So it got spun around a full 180 degrees, and it got increased in size with a scale of 1. So to prove that, I look at my side measurements. The base of that triangle was 2, doubled equals 4. The original height was 3, and its new height was 6. Here's one more example. Describe the transformations. Do you see what types of transformations? So I've got a trapezoid that, here's my original. And then the new one is here. Okay. It got, let's look at this one, went there, here, there, and there. So it got spun around 90 degrees, which is a rotation. But my original trapezoid is bigger than my little one. It got scaled by half. And I'm going to abbreviate scale factor by 1/2 to prove that the top here is 4, but the little one is 2. The length on this side was 8, but my little one was 4. And its height was 6, but its new height here, I'm sorry, I miscalculated that. My height also was moved there. Please ask questions in class. This one was a really long one. And see you later.